A human crew is bound by strict biological and cognitive limits. In modern deep space flight, the data processing requirements generated every second easily exceed the capacity of manual human analysis. When the Space Launch System propels Commander Reed Wiseman and his crew toward the Moon in 2026, the mission will act as a live testbed for a distinct operational architecture designed to solve this exact problem. Deep space navigation has historically relied on manual oversight. During the Apollo 8 mission, astronauts and ground control operated in a strict human-in-the-loop framework. The crew interacted with the Apollo guidance computer using a basic verb-noun syntax, managing a few dozen critical variables to manually execute burns and trajectory corrections. The Artemis II Orion spacecraft operates at a vastly different scale. The vehicle continuously generates telemetry from over 150,000 active sensor streams simultaneously. 4 astronauts cannot parse hundreds of thousands of data points in real time to identify the microscopic origins of a system failure. Furthermore, relying entirely on ground control is impossible. As the spacecraft travels further into deep space, the latency in Earth-based communication increases, introducing the severe risk of permanent communication loss. To survive the data density and navigate through signal blackouts, Artemis II integrates an autonomous onboard framework, a system acting as a dynamic fifth crew member. Deep space computation begins with physics. Standard silicon integrated circuits are rapidly destroyed by cosmic radiation, requiring highly specialized radiation-hardened hardware. The Orion flight computer features a quadruple redundant, radiation-hardened multi-core design, built specifically to withstand the lunar environment without data corruption. This table compares the 1960s Apollo guidance computer with the Orion flight computer. We see a jump from 2 MHz to 200 MHz, representing a 128,000 times memory increase. Apollo's magnetic core rope memory physically constrained the system to basic arithmetic and dropping tasks during overloads. Orion's gigabytes of flash memory and SD-RAM provide the computational density required to host machine learning algorithms and predictive neural networks directly on the ship. This processing layer executes massive data workloads internally. It does not need to compress telemetry, send it to the deep space network, and wait for Earthbound supercomputers to return an answer. Localizing the compute power eliminates communication latency, giving the spacecraft the ability to analyze and react to critical variables independently. The primary navigation challenge of the Artemis II free return trajectory is absolute positioning. Between Earth and the Moon, the global positioning system does not exist. As the spacecraft distances itself from Earth, ground-based tracking inevitably degrades, exposing the crew to the risk of total signal blackouts. To counter this, Orion utilizes the Autonomous Optical Navigation System, or OPNAV. This independent suite uses a body-fixed camera and AI processing to determine the ship's exact location in the vacuum of space. The Christian Robinson algorithm processes optical data by recovering a celestial body's limb projection geometry. First, it identifies background stars against an internal catalog to calibrate the camera's focal length. Next, it calculates the planet's apparent angular diameter to pinpoint its exact mathematical centroid. These raw pixel measurements are mathematically transformed into precise range and bearing angle data. The data is then fed directly into the flight computer's Kalman filter, updating the onboard state factor, the exact velocity and position of the ship, in a single non-iterative step. During the uncrewed Artemis I flight, this system autonomously processed over 1,000 images. Its performance exactly matched the strict pre-flight error models. OPNAV provides the required stabilization logic for proximity operations. It guarantees trajectory control, even if Earth completely drops off the communication network. While OPNAV looks outward to determine location, an entirely different AI architecture looks inward to prevent catastrophic hardware failure. This 2D graph shows the inherent flaw of traditional spacecraft monitoring. A system watches a single metric, like temperature, and triggers a reactionary alarm only after it crosses a hard limit. A single parameter rarely causes a vehicle loss. Modern system failures cascade through nonlinear interactions across multiple components simultaneously. To solve this, Orion integrates System Invariant Analysis Technology, or SIAT, within its analytics platform. It monitors all 150,000 sensor streams at once. By mapping over 22 billion logical relationships across the data, SEAT's analytics engine defines the baseline for normal behavior across the entire spacecraft. Processing the telemetry to build this behavioral model takes the AI just 4 hours. Manually mapping these exact correlations would take a human engineering team hundreds of years. This creates an absolute web of context. If there is a micro-fluctuation in electrical bus power, combined with a fractional shift in thermal output, neither event triggers a single threshold alarm. However, the AI recognizes the nonlinear correlation between those two distant sensors, predicting a cooling pump failure days before the hardware actually breaks. This removes the burden of manual telemetry analysis from the flight controllers at Johnson Space Center. By identifying subtle anomalies early, the AI shifts the engineering protocol from reactive emergency response to proactive system maintenance. The most fragile system aboard Artemis II is the human biology, continuously subjected to microgravity and elevated radiation exposure. The crew tracks their movement, their daily sleep patterns, and oxygen saturation using wearables. This raw data feeds into localized AI models designed to detect early physiological stress. To manage crew health directly, NASA is developing the Crew Medical Officer Digital Assistant, an agentic AI trained on extensive space medicine databases. This bar chart visualizes prototype benchmarks for the system. Using large language models, the digital assistant guides non-medical astronauts through clinical tasks, achieving an 88 as communication delays expand to 44 minutes during future Mars missions. Possessing an onboard dock-in-a-box and an instant virtual testbed becomes an absolute requirement for mission survival. Artemis II serves as the definitive test flight for human rating this specific AI software stack in deep space. Once proven, this autonomous architecture will transition directly to surface operations for Artemis IV and V. Surface exploration will rely on initiatives like the Cadre mission. This utilizes cooperative swarm robotics to autonomously map the lunar subsurface using ground-penetrating radar. The rover swarm operates using a leader election mechanism. The machines independently assign tasks based on thermal constraints, and if the lead rover fails, the swarm immediately elects a replacement without human input. Sustained lunar presence requires in-situ resource utilization. Projects like Olympus use AI-managed robotic systems to melt local regolith into solid 3D-printed ceramic structures, completely automating the construction of habitats and landing pads. Generative AI is even deployed on the administrative side, automatically parsing complex engineering documentation to verify that these robotic systems strictly comply with NASA's software safety standards. The telemetry gathered by Commander Wiseman's crew will prove whether human intuition and machine intelligence can execute a mission as a unified system. The autonomous software validated on Artemis II is the required technological bridge. It provides the independent intelligence necessary to push humanity to Mars.